My name is Chris Vanderlip, and my thesis is titled Eocene and Modern Stress Regimes at the Intersection of the Eastern Reelfoot Rift Margin and the Meeman-Shelby Fault, Western Tennessee. I'd like to start off by thanking my committee, Dr. Cox, Dr. Larson, and Dr. Van Arsdale. I'd like to acknowledge the USGS EdMat program for the opportunity to map my study area, as well as the property owners in my study area. And most importantly, I'd like to thank my wife, because without her, I would probably be stuttering drunk in a corner somewhere. My study area is 40 kilometers north of Memphis in western Tipton County. There's Tipton County right there. The basement faults of the eastern Reelfoot Rift margin pass through the study area, and they are probably accumulating right lateral strike-slip strain in the modern east-west tectonic compressive stress field, represented by the red arrows. The Meeman-Shelby fault zone trends north-northeast towards the study area from west of Memphis and shows quaternary deformation in seismic profiles. Northeast of the study area, faulting defines the Bluff lineament, a 100-kilometer scarp containing faults that also show quaternary deformation in seismic profiles. Sugar Creek is the site where Dr. Cox discovered the exposure of a thrust fault at the Sugar Creek ATV Club, shown with the yellow dot. The black box is the area of the Drummond 7.5-minute quadrangle map that was the focus of my EdMap project. And the white box is the Sugar Creek watershed map on the next slide. Zooming in to the Sugar Creek watershed, the focus on the study is on lower Sugar Creek and the Warren Quarry. The dots show the location of the ATV Club parking lot and Warren Quarry. And the next slide shows the areas of the white boxes. Richardson Landing is a small community here, and Drummond's is the nearest town, the namesake of the Drummond's quadrangle. The dot here is the ATV Club parking lot again, and three exposures, the red dots, define the Sugar Creek thrust fault. Over at Warren Quarry, the Warren Quarry anticline is exposed trending east-west. So Richardson Landing has exposures of two east-west trending structures, an anticline, which is a fold that opens downward, and a thrust fault, which is a low-angle compressional fault. Both of these structures indicate a tectonic compressive stress in a north-south direction, which is at odds with the east-west modern compressional stress. Moreover, they are at odds with the Eocene stress field, which is not particularly well constrained, but was probably oriented northeast-southwest, at least for a time. So the objectives of the research are to answer why the geometry of these structures is inconsistent with the modern and Eocene stress fields, and to assess any seismic hazard these structures may present. In the study area, the Surficial Geology exposes the Eocene Cockfield and Cook Mountain formations. Overlying the Eocene section is the Plio-Pleistocene upland complex, a terrace of the ancestral Mississippi River, and topping the uplands is Quaternary loess, a wind-blown glacial silt, and Quaternary alluvium is incised into the underlying formations. The subsurface geology pertinent to this talk consists of Eocene fluvio-deltaic sediments of the Cockfield and Cook Mountain formations and the Memphis sand below them. Here's a photograph of the Sugar Creek Fault, seen here in exposure at the ATV Club looking to the south. Note the shovel for scale. Here, the fault strikes east-northeast, west-southwest, but overall strikes much closer to east-west. What I interpret as Cook Mountain clay is thrust up over top of Cockfield sand. This quaternary sand and gravel up there is a terrace of Sugar Creek. It may be faulted or warped, and I suspect that it is, but exposure does not allow us to tell. This area up here is particularly steep, slick, and treacherous, and very difficult to clean. And that's not for lack of trying, of course. Notice this pile of limbs down here. That took quite a bit of effort to bring just those down. The Warren Quarry anticline strikes east-west. The northern limb dips gradually to the north, and the southern limb dips more steeply to the south. The anticline has loess faulted down into the crest of the anticline, and these down-faulted bodies, or grabens, strike parallel to the anticline along its axis. The methods I used in the study include field mapping and borehole interpretation. The Eocene exposure is mostly in creeks along the bluffs, so borehole interpretation allowed me to fill in gaps further into the upland. Subsurface structure contour maps and cross sections were developed from borehole pics of the elevations of underlying Eocene formations, mostly using shallow 100-meter deep wells, and the discussion here is based on a reconstructed Eocene section with the effect of post-Eocene erosion removed. Fracture data collected in the field was analyzed for stress orientation interpretation. And for brevity, I will not be discussing geomorphic analysis, but will briefly discuss the results of OSL and carbon-14 dating in my conclusions. We'll first look at the surficial geology in the study area, and then I'll discuss the subsurface geology. We'll look at Sugar Creek first, the area in the white box. This map shows the surficial geology of Sugar Creek. The yellow dot, again, is the ATV Club parking lot. The fault is shown with teeth on the hanging wall, which is the upthrown side of the fault, if you don't speak geologist, and the downthrown side, the footwall, is on the south. Bedding orientation in the area varies, but away from the fault, the Eocene strata are typically subhorizontal with shallow dips of, for example, 4 and 6 degrees, and these shallow dips are assumed to be depositional. So now we'll zoom in on these white boxes. In the area around the fault, bedding dips more steeply and consistently to the north and northwest. Here you have 41 degrees to the north, and over here you have dips of 15, 30, 18, 19 towards the northwest. The fault itself dips about 25 degrees towards the north-northwest in the east side, and over towards the west it dips about 30 degrees straight to the north. 3 exposures constrain the fault for half a kilometer. The fault doesn't penetrate the north wall of this meander here, so we know that it must continue westward, and I project its extent into the western tributary there, where it may be dying out into an anticline, which is exposed in the creek. The bedding around it may reflect this fold as well. Note the huge change in sinuosity from here to there on that tributary. This is likely due to the change in lithology across the fault. Now let's have a look at the area around Warren Quarry. At Warren Quarry, the axis of the anticline is exposed across the quarry floor, shown in the map by the loess in the graben, which I'll enlarge in a moment. The graben is exposed in Sullivan Road Creek, and an east-trending topographic low suggests that it may continue further and has influenced the topography there. So zooming in on the quarry, the bedding exposed there dips gently to the north and a little more steeply to the south. And even the overlying unit, this overlying red gravel, this overlying gravel, this red unit, is steeply tilted. This is probably due to it having been dropped into the graben rather than being a dip on the southern limb of the fold. The east-west trending structures I infer to be related due to their similar orientations and their fact that they are consistent with a north-south compression direction. I call them the Richardson Landing Fault Zone. The red box here is the area of this map to the right. The Sugar Creek Fault is shown with red dots signifying the exposures, and green dots signifying the inferred locations, this being the anticline and this being a seismic line. The Warren Quarry anticline is identified by the graben and the topographic low there. It projected to the east, it should cross the creek in a couple of locations. However, I was unable to investigate as the property owner was adverse to my presence, and it's probably too high in the stratigraphy anyway to expose anything significant. However, in Sugar Creek, further to the east, the creek takes this little east-west jog here, and in that spot there is an anticlinal upwarping present there in the Eocene that's exposed. It's projected further east based on topographic lineaments, as is the Sugar Creek Fault. The geometry of the Warren Quarry anticline is consistent with a fault propagation fold model with an up on the north blind fault at depth, which would be parallel with the up on the north Sugar Creek Fault. Now I'll discuss the fracture data that I collected. The data are presented with Rose diagrams at left and stereo nets at right. Rose diagrams show the azimuth of fractures in compass orientation, and the number of fractures is shown by the relative length of the bars. The stereo nets show the same data, but as a projection of the fracture plane onto a hemisphere, like looking down into a bowl. If you're not used to looking at these type of diagrams, just stick with me and hopefully it will make sense. Here I show data from Warren Quarry. Although there's a lot of scatter in the data, there are hints of various sets, but the most prominent set is oriented north-south. These fractures, if they are extensional fractures, are parallel to the compression direction that formed them, and therefore are evidence of north-south compression, consistent with the orientation of the Richardson Landing Fault Zone. In the bottom row, I show the same data, but with the graben parallel fractures removed, because I interpret these to be due to localized bending moment extension, as extension occurs along the axis of the top of a fold, something like that. Removing these makes the north-south trend clearly the dominant trend. The fracture pattern at Sugar Creek is more complicated, more complex, containing multiple high-angle fracture sets as well as low-angle sets, but dominant trends support an interpretation of north-south shortening. Fractures from the southern Drummond's quadrangle south of the study area show strong trends that are slightly off from what we see at Sugar Creek and the quarry. It's possible that those trends are regional and contributing to the strong northwest-southeast and northeast-southwest fracture trends seen at Sugar Creek, while the north-south fractures may be more local and typical of the study area. Now we turn our attention from the Surficial Geology to the Subsurface Geology. So I'll show the stratigraphic column again as a quick reminder that the relevant formations are the late Eocene Cockfield Formation, Middle Eocene Cook Mountain, and early Eocene Memphis Sand. Here I present the area of the Drummond's Quadrangle, showing the structure contour for the top of the Cook Mountain Formation. The red square is the area of the Sugar Creek watershed map. Gray and red dots present well control locations. Again, most of the wells available are only 100 meters deep. Gray dots represent wells where the elevations are directly interpreted from the top of the Cook Mountain. In red dot wells, the top of the Cook Mountain has been eroded by the Mississippi River, and the surface has been reconstructed using the elevation of the underlying Memphis sand and the consistent 60-meter thickness of the Cook Mountain in deeper wells to the north, east, and south of the study area. The contours show a north-south trending structural high, which I call the Drummond's uplift, and a north-south trending structural trough to the east of the Drummond's uplift. Now let's discuss an interpretation of the deformation in the study area. far as the two east-west trending surface structures in the Richardson Landing Fault Zone are concerned, the Sugar Creek Fault is a north-dipping thrust fault, and the geometry of the Warren Quarry anticline is consistent with a fault propagation fold dipping to the north. These geometries are consistent with the hypothesis that the structures are splay faults off of a master fault at depth. The next slide shows a conceptual north-south cross-section of the hypothesis through the study area, shown in the gray boxes there, and crossing the fault exposure. The inset shows the location of the seismic line, the cross-section. This black line here is the Sugar Creek Fault, and this line here is the projection of the Warren Quarry anticline. In the cross-section, elevation is shown here, and distance is shown here. The Mississippi River is shown right here, and the topography is this line. This is the Mississippi River Bluff, Sugar Creek there, and to the south. The cross-section shows the lithologies of the exposed Eocene at the Mississippi River Bluff and at Sugar Creek based on a reconstructed Eocene section with the effect of post-Eocene erosion removed. Here you can see the Sugar Creek Fault as a thrust fault and the Warren Quarry anticline with a propagating fault at depth, and these faults in turn splay off of a master fault at depth. This master thrust hypothesis is consistent with the geometry that can be seen on faults and pop-up structures associated with compressional bends and strike-slip fault systems. So shown here is a model modified from Pratt 2012 that compares the New Madrid and Rift margin faults, shown with black lines, with the pattern of faulting from sandbox models of pop-up structures from McClay and Benora 2001, shown with red lines. The study area is shown with a green dot, and small gray dots show the pattern of New Madrid seismicity. The inset shows the location of the cross-section through the model. The location of the Richardson Landing Fault Zone is consistent with the thrust fault here and in the cross-section there. This model shows that it is possible to get low-angle thrusts at this strike in the modern stress field. So now we'll shift gears from my interpretation of the Richardson Landing Fault Zone to my interpretation of the rift margin parallel faults from subsurface data. Higher dips between wells are consistent with the Meeman-Shelby faults passing through the study area. With some additional seismic data, I infer that the west Meeman-Shelby fault is down on the west through the study area as it is to the south. This is shown with a tick on the down-thrown side. The Meeman-Shelby fault, however, I infer to change sense of displacement across the Drummond's uplift, going from down on the east to down on the west. So finally, let's take a brief look at the seismic data. The map on the left is the study area and to the northeast. The gray box is the northern Drummond's quadrangle. Available seismic lines include two industry seismic lines, the red and purple seismic lines, and a river seismic survey shown in yellow. Areas of structural complexity shown with colored boxes define an area, a zone of faulting possibly related to the Reelfoot rift margin. The faulted area shown in the red box is directly under Sugar Creek, which is shown on the seismic line with the green dot. The yellow and green boxes show faulted areas suggested to be two separate fault zones by Howe 2015, and I suggest that they are part of the same fault zone, which the survey crosses over twice around the bend in the Mississippi River. It's possible that this zone is encountered again in the northeast in the faults shown by the purple box. Note that in the deep industry seismic lines, this zone overlies the step in the basement that represents the Reelfoot rift margin.